We will look at concavity and the second derivative test. The objective will be to determine intervals on which a function is concave upward or concave downward. Find any points of inflection of the graph of function, and then we'll apply the second derivative test to find relative extrema of the function. So let's understand, well, maybe from a graph, what I mean by function, concave up or concave down. Then also inflection points. So I wanted to first show you from a graph what's really happening, or what do we mean by a graph is concave up or concave down. So let's analyze this graph. If you look at this portion of the graph here first, okay, somewhere here, you will notice that that graph is concave down. I mean, when we spoke about parabolas, we already know concave up and concave down. So this portion of your graph here is concave down. But if you look again at this side of your graph, yeah, this side is concave up. So some graphs will have concave down, concave up. Now the point somewhere on the graph where it made that transition from concave up to concave down, let's say some point around here, okay, that point is where we call our inflection point. That is my inflection point, somewhere over here. So there are many things we can talk about this graph. Notice that when it reaches maximum point here, which we spoke about, and a minimum point here, the slope of the tangent line is 0. Okay. So if we look at another example, so this picture here had both concave up and concave down. If we look at a different example or a different graph, such as this one here, yeah, you will notice that this is just all concave up. Yeah. So this graph is just concave up. And there is no inflection point here. So we have seen from the last section, locating the interval in which a function f increases or decreases helps to describe the graph. In this section, we'll see how locating the intervals in which f is increasing or decreasing can be used to determine where the graph f is concave upward or downward. So by knowing if it's increasing or decreasing, now think about that, because if a graph is increasing, okay, it could be increasing concave upward, such as this one here, it's still increasing, okay, or it could be increasing concave downward. So this one here is still increasing. This one is increasing, okay, And the reason we say it's increasing, because if you look at the slope of every single point here, the slope of every one of those lines is a positive number. Okay, so it is increasing here, and it is concave up. Okay, here it is increasing, and it's still, but now, right, concave down. Now you can imagine about this is that, for example, if you look at a sort of the parabola, what parabola will this make? Well, the parabola here would look like this, and the parabola here would look like this. And that's why we say this is concave up and this is concave. It's still increasing. Concave is supposed to be concave up. Yeah, concave up. So they're both increasing, but one is increasing concave down here. Sorry about that. Okay, because if you look at that parabola, the parabola looks like a concave down parabola. And that's our goal, right? So concave increasing here. Once again, if you look at the slope of any one of these lines here, they're positive. So that means the graph is increasing. Any one of these little tangent lines. So here we have the definition of concavity. Let f be differentiable, so make sure that your graph is differentiable. Okay, we have to make sure that the graph is differentiable on an open interval. The graph f is concave upward on the interval when f prime is increasing, and it's concave downward when f prime is decreasing on the interval. So those are some important points you will see as we work through some examples. So what we're going to do is list this test for continuity, concavity. And I've listed that here, and then we'll look at examples. So basically it's saying if f double prime is greater than 0 on an interval, the graph is concave upward. And if double prime is less than 0, meaning it's negative on some interval, then the graph is concave downward. So let's look at an example now. Example. So let's determine we'll determine the open interval in which the graph of f of x equals x to the fourth minus 4x cubed is concave upward or concave downward. Okay. Now, as we saw before from either one of these pictures here, okay, we'll be able to find the first derivative will tell us where the extremes are. And then the second derivative, which we're seeing from here, will tell us the concavity. So we have to find first the first derivative and the second derivative. So if we look at our function, which is x to the fourth minus 4x cubed, right? F of x is equal to x to the fourth minus 4x cubed. Okay. We can see that f prime of x, which is the first derivative, will be 4x cubed minus 12x squared. So this is the first derivative. And then if we find the second derivative, okay, meaning think of this here as your function, okay, and take the derivative of this. So f double prime of x would now be 12x squared minus 24x. So we found our first derivative and our second derivative. Okay. So if we take the second derivative now and we set that equal to 0, okay, because if we look back here at our test for concavity, we said that if f double prime is greater than 0, it's concave upward on the interval. So we're talking about f double prime. So f double prime of x is 12x squared minus 24x. So f double prime of x equal 0 means that 12x squared minus 24x is equal to 0. We can factor out 12x, so we have x minus 2 is equal to 0. And then we have two factors. Yeah. So here we have 12x is equal to 0, and we have x minus 2 is equal to 0. So x is equal to 0, and x is equal to 2. And that kind of breaks up what I like to do at this point. A suggestion here, if you draw the number line, okay, if you draw a line such as the number line, and you put those points 0 and 2, and what is this interval here? Well, this interval will be from negative infinity to 0, okay, open interval. This interval here will be from 0 to 2. And this interval here will be from 2 to infinity. So what I'm going to do is create a table just so it's a little bit clearer. So here's my interval. Okay. And the first interval we have would be x is less than 0, but greater than minus infinity, which is the same as this interval here. Okay. Our second interval we have is x less than 2, but greater than 0, which is this interval here. And the third interval we have is x less than infinity, but greater than 2. And then what we're going to do is pick a test value. Okay. Meaning pick a number in this interval here. Pick a number in this interval. So pick any number here, test value. Well, we could pick x equal -1. And the same thing we'll do in this interval here. Pick a test value in that interval. We can pick x equal 1. Any number, if you wanted, you could have picked a fraction, but I'm sure you wouldn't want to plug a fraction in. And then pick an interval, a number, a test value in this interval. So you can say x equals 4. And remember, the definition says that we should now plug this in to f. Right, if you go back to the definition, it says we'll plug this into f double prime. Okay. f double prime. Okay. Let me finish drawing out my table here. And we want to check the sign of f double prime of x. So basically what I'm doing, f double prime of x, we know, is 12x squared minus 24x. 12x squared minus 24x. So what is f double prime of negative 1? Well, this is 12 times negative 1 squared minus 24 times negative 1, which becomes 12 times 1 plus 24. And we don't care to know the number. When you add this, it's going to be greater than 0, meaning it's positive. That's all we care to know about. If it's positive or negative, we don't care to know the physical value. So that's why over here, I wrote it's greater than 0. Okay. You will notice if you do the same thing for f double prime of x, which we know is 12x squared minus 24x. So what is f double prime of 1? You will get 12 times 1 squared minus 24 times 1. So this is equal to 12 minus 24. We don't care to know the value. This is going to be some negative number. So it's less than 0. So f double prime of x is less than 0. F double prime of 1. So f double prime of 1 here is less than 0. And then if you do the same thing for the third interval, f double prime of 4, okay, you will see that f double prime of 4 for us is greater than 0. And now we make our conclusion. Okay. The conclusion, it tells us from here, if it's greater than 0, then the graph is concave upward. So it means here, this graph is concave up. And this portion here, since it's greater than 0 also, it's concave up. When it's less than 0, it is concave down. Okay. So what we're expecting to see, what we're expecting on this graph, as a rough sketch, is that on the interval negative infinity, okay, let's say here. Between negative infinity to 0, we have our graph is concave up. So somewhere over here, somewhere in this region here, from negative infinity to 0, the graph is concave up. So we're expecting our graph to look something like this. And then between 0 and 2, our graph is concave down. So we're expecting our graph to look something of that. And then from 2 to infinity, our graph is concave up again. Okay. So we'll see later on, okay, if it's decreasing or increasing. And that's when we'll use the second derivative test to find a relative min or relative max. So we had said at the beginning of my introduction here for this lesson that we have something called inflection points. Okay. So now I will show you how do we go about finding those inflection points. And I give the definition here. Let f be a function that is continuous. So very important again, it is continuous on an open interval. Okay. And let c be a point on the interval. So we're looking at some x value, c. If the graph f has a tangent line at c, f of c, okay, then the point is a point of inflection of f when f changes from concave upward to concave downward. Okay. So what it's really saying is that if we have some graph, here's a graph that's concave up, but then it changes to concave down. Okay. My graph changes to concave down. Then this point here where it changed from concave upward to concave downward, this point here is the inflection point. Okay, that point here on the, if this was the x-axis, okay, this point here is your c value on the x-axis. And the point on the graph, if this is f of x, this point will be c comma f of c. So that's what our definition is telling us. So if we go back and look at that example we're just doing, we had f of x is equal to x to the fourth minus 4x cubed. And we saw that the first derivative, f prime of x, was equal to 4x cubed minus 12x squared. And we saw that f double prime of x was equal to 12x squared minus 24x, right? Those are the values we got from up here. Okay, we're given f of x, f prime, f double prime. All right, those are where I'm getting those values from, or those functions. Now, if we take f, when we took f double prime and we set it equal to 0, okay, when we took f double prime of x and we set that equal to 0, we got x equals 0 and x was equal to 2. Okay. So these here are what we call the possible possible points of inflection. Okay. Possible points of inflection. So by testing the interval, you can conclude they'll both be points of inflection, because we saw when we did from negative infinity to 0, the graph was concave up. Okay, from negative infinity to 0, the graph is concave up, and then the graph became concave down. So here my C value here was 0, concave down, and then the graph came concave up again. Okay, my C value here is 2. So these points here are points of inflection. Yeah, and to find the actual point, you would do what is f of 2. Okay, that will give you the y value, and here f of 0 will give you the y value. So this point here, the point will be 0 comma f of 0, and the point here will be 2 comma f of 2. So that's how we'll find our inflection points. We also said in the objective, we'll look at the second derivative test to find relative extrema of a function. Okay, so let's look at the second derivative test and the definition, and then we'll explain what that is. So we have the second derivative test, the theorem. If f double prime of some value c is greater than 0, then f has a relative minimum. And if f double prime is greater than 0, we have a relative minimum. And if it's less than 0, we have a relative maximum. Yeah. So let's look at examples, and we'll work through from an example. So I want to find relative extrema of the given function. So we'll find, let's find f prime of x will be minus 15x to the 4th plus 15x squared. Yeah. So if we want to find our critical numbers, okay, we'll see that f prime of x equals 0. So this becomes minus 15x to the 4th plus 15x squared equal to 0. So here we can take out a 15x squared, and that will give us negative x squared plus 1 equals 0. So this tells me that 15x squared is equal to 0. Negative x squared plus 1 is equal to 0. So here we have x squared is equal to 0. So x is equal to plus or minus square root of 0. So x is equal to 0. Here we have 1 is equal to x squared. So plus or minus square root of 1 is equal to x. So x is equal to plus or minus 1. Okay. So you can see that x equals 0, x equals minus 1, and x equal 1 are the only critical numbers okay, of f. But by finding the second derivative, okay, f double prime of x will be the derivative of this. Okay, so that will give me negative 60x cubed plus 30x. Okay, right? Maybe I should write back what f prime is. F prime of x we found to be minus 15x to the 4th plus 15x squared. So f double prime of x will be minus 60x cubed plus 30x. And if we set f double prime of x equal to 0, this becomes minus 60x cubed plus 30x equal to 0. And if we solve this, we could take out 30x, and that will leave us with minus 2x squared plus 1. So this tells me that 30x is equal to 0, and minus 2x squared plus 1 is equal to 0. And clearly you can go through the steps if you want to find x. Yeah. So if we make a table to see what it looks like, I always find a table to be more simplified. Okay. So here we have our point now. Okay. Then we have, well, the first point we have would be these points here, right? Those are x values. So the smallest one first, when x is -1, okay? And if you plug that -1 into the function, you should get -2. And then we have when x is 0, we'll plug that into the function, we should get 0 also for y. And then the third x value we have is x is equal to 1. So when x is 1, if we plug it in the function, we get 2. So I'm going to show you how I'm getting at least these values here, okay? Let's do one of them. So we said that x is equal to 1. And we knew that f of x, okay, f of x is equal to minus 3x to the 5th plus 5x cubed. So f of 1 will be minus 3, 1 to the 5th plus 5 times 1 cubed. So this becomes minus 3. This is just 1 plus 5. This is just 1. So here we have minus 3 plus 5, and that is equal to 2. And this is the value I'm writing here. Okay? So you can do the same thing what happens when x is 0. You could do the same thing when it happens as x is 1. Okay? You could finish up those as exercise. Now, we want to know the sign of f double prime of x. Okay? So what is f double prime of -1? What is f double prime of 0? And what is f double prime of 1? So where am I getting these values? Okay, this value was the value we solved for. This value was the x value we solved for. Remember, we have 3 x values. X equals 0, x equals 1, x equals -1. Those were the 3 values we obtained. And finally, our conclusion, if we may, conclusion. So we said if f of -1 is greater than 0, this is a relative minimum. Okay, go back to the definition. If it's greater than 0, it's a relative minimum. If it's less than 0, it's a relative maximum. So here's a case, okay? This one here, we knew is equal to 0, and this one here we know is less than 0. So this will be a relative maximum. And since it's equal to 0 here, the test fails. Okay, our test fails. So because our test, the second derivative test fails at 0, 0, since f double prime, okay, test fails at 0, 0, you can use the first test, you can use f prime, the first derivative test, and observe that f increases to the left and right at x equals 0. It's neither a relative minimum or a relative maximum. Okay. So when you look at the graph of this function, I'll draw a rough sketch for you so you'll see what's happening. Just a rough sketch. So you'll see the graph of this function here comes down, goes back there, then goes up and comes down. Okay. So you'll notice at this point here, this point is -1, -2. Okay. This point here is the point 1, 2. And this point here is the point 0, 0. So 0, 0 is not a minimum. Okay. It is not a relative minimum or a relative maximum. So that is what this section is about, to show you how to find these points. Now you should be able to put all of them. I can ask you all of these in one particular question. Okay. I could ask you, where's the function increasing? Where's the function decreasing? And that's really a summary, which we'll do in the next 2 sections. We'll summarize everything. So far in each section, we're just looking for little techniques, how to find things. So this concludes this section. Okay. You should try a few examples and we'll look at the next section, which will talk about limits of infinity.